we define the propagated error delta of y. So the triangle here is, you read it as delta. It represents the change in y. So delta y equals the function evaluated at a plus delta of x, so the change in x, minus f of a. And in the textbook, we use dx instead of delta of x. They represent the same thing. Okay, so dx here equal delta of x, and it's just the change in x. Now, sometimes it's not that easy to calculate the propagated error f evaluate at a plus dx, and then you subtract f evaluate at a. So we usually will estimate delta of y by the differential dy. And that's how the differential can be used to estimate error. Okay, so we can use differential to estimate error. And remember, dy is just f prime of x times dx. And in this case, we are talking about the point A. We just remove this x and call it our A. Evaluate f prime at A, and then do a multiplication. Sometimes this is much easier to estimate. So let's take a look at an example. Suppose the side length of a cube is measured to be 5 cm. And what it's telling us is the point of reference A equals 5 right here. And an accuracy of 0.1 cm. What it's really telling us is the change in x, because it's an accuracy, is 0.1. Okay, at most you can change x by 0.1. Those are the error of the measurement, because we're talking about accuracy here. Now, given this information, and it's a cube, we want to use a differential to estimate the error in the computed volume of the cube. So how does it work? First, we need to know, okay, what is the volume formula in terms of the radius, right, or the side length of the cube. So if, let's say, the side length is x, and the volume formula to calculate it is just x cubed. Now, if you prefer to use y, because all the formulas is in terms of y, that's fine. You just change v to y, and y equals x cubed. And then it's easier for you to kind of understand. So then instead of talking about dv, we're talking about dy, differential. So the differential dy, according to the formula, is f prime. Okay, so what is f prime here is 3x squared times dx. Now we can evaluate dy. So dy, in this case, at the point A, right? A is 5 or x is 5. It's just 3 times 5 squared times dx is 0.1. So the error is 7.5. And what is a unit? Oh, you can think about it. X is, the unit for x is cm. X squared, so cm squared. But be mindful, dx, the unit of dx is 0.1 cm. Okay, so cm squared times cm is cm cubed. And that's how you know this is the estimate of the error in the volume. Okay, and again, if we're talking about accuracy, you can even argue dx is plus minus 0.1, and you can even say dy, right, the change in volume is plus minus 7.5. And that is the estimate, the differential to estimate the error in the volume in the computation. Now, how does it compare to the propagated error, delta of y? Okay, so we will take a look. So part A, here we find out the estimate error is plus minus 7.5. So let's see the actual error, B. Okay, by definition, delta of y equal the volume at, okay, so the volume at A, so phi, plus dx 0.1. And you subtract it at f of phi. So what it really means is you calculate the volume at 5.1, okay, cubic, and you minus 5 cubed. And that is the actual change in the y, or in the volume. So then you use a calculator. We get 7.651, and it's still cm cubed. And then you also want to calculate 4.9, right? So dx is negative 0.1. So you plug it into the formula again. F, now this case is phi minus 0.1, and that's how you get 4.9 minus f of phi. So it's just 4.9 cubed minus 5 cubed. You get negative 7.351, and the unit is cm cubed. So in either case, if you take a look, okay, the estimated error plus minus 7.5 is very close to the actual error. Okay, 7.6 and minus 7.3, or minus 7.4. So in this case, we can see how the differential is very close to the propagated error, and how we can use the differential dy to approximate delta of y.